I've decided to make you a video about how to deal with a curved graph. It is a process that I will call linearization. So if you hear that term, it just means taking any curved graph that we get in the lab or you see in any other place and doing what we can to make it a straight linear graph. So for me to be able to start talking about it, we need to refer to this graphical methods reading that I posted. And once again, I talked about the first 2 pages, and then that just went over how you deal with a straight line graph. But then the last 3 pages, I did go over quickly, but I do want to go over them a little bit more. And then I would actually like to, once again, show you how to deal with that in the pendulum lab, and more specifically the period versus length graph, which does have the relationship that should be curved. So here we are. Pages 3, 4, and 5 have different curved graphs. And the first graph that you will see is a curve that looks like this. It's called a hyperbola. And whenever you have a curve like this, it is what is called an inverse function, which means that as one increases, the other decreases. And so as one goes up, the other goes down. So when you plot those points, that's how it's going to look. However, if we want to make some sort of straight line graph with some form of these variables, what we actually need to do is do the inverse of one of the variables. And in this case, we'll typically do the x-axis. You could do the y-axis as well, but let's just do the x-axis so we're all on the same page. And so what I will do is I will take all of my v values, and instead of having them be the v values, I will have them be 1 divided by the v values. And when I plot that, what you will see is you have p, which is what we had before, but then instead of v, you have 1 over v, and then you have that straight line graph when you plot it. So since we have a straight line graph that goes back to y equals mx plus b, and we can plug in our y and our x into the equation, and we're now left with p equals m times 1 over v plus b. So this is the y, and this is the x. And in this case, b is 0 because the line crosses right through the y-axis, y-axis. And as far as the slope goes, we don't have any numbers, but we could figure that out if we wanted to. But Logger Pro is going to figure that out for us for now. All right, the next curve is the top opening parabola. It's just a parabola that goes up like this, and the top is open. And when we have a parabola like this, this is showing that one of the variables is increasing at a faster rate than the other. In fact, the variable that is increasing at a faster rate is the d variable, because the line is curving in the direction that d is going, the y is going. So the only way I could get some sort of straight graph from that is to make this axis increase faster as well. So I would have to do something to this variable and plot whatever I do to this variable on the x-axis to get a straight line. And in fact, the thing to do is to plot d versus t squared. And in doing so, I now have values that are not just t, they're t squared. So every t value, it's squared, and so there's a faster increase. So when I plot it, I get d and t squared, I get a straight line, and then my y equals mx plus b equation is now d equals m times t squared plus b. D is the y, t squared is the x. And since we have some numbers here, we can figure out the slope, and the slope is 0.80 meters divided by 0.50 seconds squared, and that equals 1.6 meters per second squared. We see that the y-intercept is 0 because that's where it crosses the y-axis. It's 0, and so b is equal to 0. So we're left with this equation that it's d equals 1.6 meters per second squared times t squared. Okay, now the graph that we care about for this lab is the next one. It is a side opening parabola. So it is a parabola that's open on the side. And in this case, once again, because it's curved, one of the variables is increasing at a faster rate. And this time, it's the h, because the line is curving in the direction that the h goes. So, kind of like we did with the last graph, we're going to have to make the d-axis here, or what's on this axis, increase at a faster rate. So this time, we will actually plot d squared versus h. And in doing so, we now have these d values that are squared, and so when you plot them, they increase faster, and you're left with a straight line. And once again, we have some numbers here, so we can come up with a full equation. But for our y equals mx plus b, we now have d squared equals m times h plus b. D squared is y, h is x. And then you can calculate the slope like so, and you get 2.5 centimeters squared over 5.0 centimeters, which is equal to 0.50 centimeters. And you plug that in for the m, and you see that b is equal to 0, because that's where the line crosses the y-axis for the y-intercept. And so you're left with an equation of d squared equals 0.50 centimeters times h. All right, so that's how you generally deal with all these curved graphs, and you will be dealing with them more frequently after this lab, and you'll deal with all of them after this lab. But let's look at our period versus length data. So I showed this in class yesterday, but I think it's important to see it again. So I'm going to pull up my Logger Pro graph, and what you see here is period versus length. My lengths are here, my period is here. Now I just want to look at these numbers and let's analyze them a little bit. My length numbers don't go up by even increments. In fact, each succeeding number goes up by more than the number before it. So we go from 1 to 4, we go from 4 to 9, 9 to 16, 16 to 25. Each time that's a bigger increase. Now when you look at the period numbers, you'll see that this is a constant increase. Every single time the period increases by 6. So if one is increasing constantly and the other is increasingly, exponentially, then we definitely get a curved graph. Let me do this. Okay, that's better. So here are my points plotted, and as you can see here, you can definitely see that they're curving. You may not see this as well on your graph, simply because you may not have a large enough range, or you just have some experimental error. Whatever the case may be, you still want to go through this process. So let me put a linear fit so you can definitely see the curve. So I have a point down here, I have points up here, and then I have another point right here that's down below. So these points are curving around the line. So this information that's given to me for the linear fit doesn't really mean anything, because the linear fit is not a representation of those points. But I do have an important value in here. It's called the correlation. The correlation in here is 0.9811, which actually seems kind of good. Why? Because the best correlation you can have is 1. So anything closer to 1 is better. The worst correlation you can have is 0. And the other best correlation you can have is -1, and that's if you have a line with a negative slope. So right now we have this 0.9811 correlation. We need to see if we make an adjustment to this graph and do another linear fit, can we get a higher correlation? So seeing that I have this side opening parabola, what I will need to do is I will need to square the period values. So this is what I do. I go up to the top and I click on Data, and I do a new calculated column. And in this new calculated column, I'm going to give the column name the name of what the variable is going to be, and it's going to be period squared because I'm squaring period. And the short name will now be t caret 2. So that the caret is just an exponent. And then since my units of period are seconds, I'm going to have the units of period squared be seconds squared. Now here's the most important step. Here's the expression. I need to tell my column what kind of math to do. So I am squaring periods, so I select the variable that I'm doing the math to, and I do period, and then I do caret 2, and now I've told Logger Pro how I want this column to calculate. And as you can see, I have period squared values here, period values here, and all these squared values are square of those values. That's exciting. Now as you can see, the graph hasn't changed, but I can make a change to it. So I click the y-axis because that's the variable that I want to plot differently. And instead of plotting period versus length, I'm going to do period squared versus length. And when I do that, I get these points that follow a nice straight line. This will not happen for you perfectly because you do have experimental error. I made up these numbers to work out perfectly to prove a point. But when I do a linear fit, you'll see that I now have a nice straight line, and that straight line is going through every point perfectly, so I have a correlation of 1. And in here, I now can use the slope and intercept information and this equation information because this is information for a linear fit, and a linear fit for this particular graph is the way to go. So I have t squared as my y variable, and it's going to be equal to m, and m is my slope, which is 36.00 seconds squared divided by m, which is meters, and then times L, which is the x variable, length, plus B, which will be 0 seconds squared. So ultimately my equation for my y equals mx plus b function would be t squared equals 36.00 seconds squared per meter times length, or L. All right, so for your lab report, the equation you will need for the period versus length relationship is the equation you get from this graph. Although I do want you to include the period versus length graph before it has been fixed, but I don't want any equation from that graph. I only want it from this graph. So I hope this was helpful for what you need to do for the lab. And I also hope this is helpful for what you will need to do for your next assignment, where you'll actually just be graphing and you'll be fixing curves and linearizing them and coming up with a mathematical relationship. All right, well, that's all I have for now. Best of luck as you linearize. Whoop, whoop.